If Taylor series allows us to approximate functions of one variable with a tangent line, parabola, or polynomials of higher order, what about functions of more than one variable? Can we approximate functions of more than one variable, which are maybe complicated surfaces with planes, quadratic surfaces, and other such higher order surfaces? Well, that's going to be the content of this video. And as always, if you want to go through the full course on the introduction to differential calculus, please visit www.dsigma.in, where we endeavor to bring math and well-being together, which means that we understand the hardships and challenges you go through during your learning journey. Whether you're a college student or a new graduate or somebody who's looking for a job and is reskilling through our platform or through any other means, if there's any way we can help you with, if you need an ear to listen to you, if you need somebody to be by your side as you go through your life's challenges, we're there for you. Do reach out to us. Let's get back to the video. All right. So if you watched the previous video, we looked at a Taylor series approximation for a function of one variable, which is of the form, I'll just repeat that for you. Let's say we have a function f of x. The Taylor series approximation, and we're assuming that the function is differentiable for now for any order that you care about, is of the form f of x naught plus the first derivative evaluated at x naught times x minus x naught. So that's the linear approximation. And this is what characterizes a tangent line at the point around the point x naught. So this is an approximation, a polynomial approximation to the function in the vicinity of the point x naught. So that's the key point around which we are expanding, around which we are looking to approximate the function either by a straight line, or if I take a higher order term, f double prime x naught divided by 2 factorial, then that's a quadratic approximation to the function. And we can extend this to nth order, and I can write this as the nth derivative of the function evaluated at x naught divided by n factorial times x minus x naught to the power of n. Now, what about a function? Can we generalize this idea to functions of more than one variable? So let's look at a function of two variables. And if you remember, one of the examples we've been working with in the past videos, we looked at a function of the form fxy equals x cubed e to the power of minus x squared plus y squared. And this sort of, if you were to plot it, would look like a three-dimensional surface. So this will be the z coordinate, like this. That's the z coordinate, and then you have the xy plane, where as x and y vary, the z value of the function varies. Right? This is what we mean by function more than one variable. Now it turns out that we also have a generalization of the Taylor series to functions of more than one variable, and this Taylor series is motivated by the same idea with which we worked out the Taylor series expansion for a function of one variable. In other words, let's say I have a function of two variables, and I care to approximate this function around, let's say, the point x naught comma y naught. Then we can write this in the form of some constant a naught plus perhaps another constant, which is a1 x minus x naught, plus maybe another constant. Let's call that b1 y minus y naught, plus another constant, which we can call, well, let's say a2, and this should be x minus x naught square, plus b2 y minus y naught square, plus, now notice that this is somewhat like a linear approximation of the function. We'll see geometrically what this means, and maybe take a guess at what kind of a geometrical surface would, if I were to truncate the expansion right here, what kind of a geometrical surface would it represent? Likewise, if I were to truncate my expansion here, what kind of a geometrical surface would it represent? But notice that here, I have two powers of x minus x naught. Here, I have two powers of y minus y naught. But given that we have two variables, x and y, I can also construct a term which is degree 2 by multiplying, maybe using something like c2 x minus x naught times y minus y naught. Now, this is also a kind of a quadratic term. It has one power of x and one power of y. So as we generalize this kind of an expansion to to functions, the Taylor series expansion for functions of more than one variable, we'll also see that in addition to these kind of regular terms, we also have these kind of cross terms. And likewise, you can extend to higher order. So let's for now truncate ourselves to the second order approximation. Now, how do you think we can identify these terms? Now, if if you've gone through the course on the Introduction to Differential Calculus, which is available on www.dsigma.in, you'll notice that we generalize the idea of a derivative of a function of one variable to what are called partial derivatives, which is if you have a function of more than one variable, let's say in this example, we have a function of x comma y, and we hold one of the variables, say y constant, I can study the variation of this function as I vary x. That is, I hold y constant and I only vary x, and I study the variation of this function. And this idea is encapsulated by what are called partial derivatives. So let's say I want to figure out the value a naught. Now, one of the things I can do is notice that all of these terms here have x minus x naught, y minus y naught, something which is varied around x naught, y naught. So what if, again, I do something which I did last time, and I look at order 0 terms and study the behavior at x equals x naught, comma y equals y naught of the left-hand side and the right-hand side of this expression. So on the left-hand side, if I evaluate the function at x naught, y naught, I'll have the value of the function at x naught, y naught. And on the right-hand side, if I set x equals x naught and y equals y naught, what will happen is I'll have the first term a naught from here, whereas all the other terms, this one evaluated at x equals to x naught would be 0. So this will become 0. This evaluated at y equals y naught will be 0. Likewise, all these terms will just be 0. So we'll have this as 0, which means just evaluating the function at x naught comma y naught will give us the first constant of expansion, which is a naught. So a naught would just be f of x naught comma y naught. Now, how do you think we can evaluate a1? Well, one of the things we can do is I can take the partial derivative of the left-hand side of this expression with respect to x, evaluate that partial derivative at the point x equals x naught. And likewise, I can take the partial derivative of the right-hand side of this expression with respect to x and evaluate it at x equals x naught. Let's see what that leads us to. So if I differentiate the left-hand side, so I'm going to write this as order 1, but we'll have more than one term for order 1. So let's say order 1, and we're going to evaluate tau f, tau x. So notice that this is a function of x comma y, but we're going to take the derivative and evaluate this at x equals x naught, comma y equals y naught. On the right-hand side, if I take the partial derivative, the first term is just a constant. If I take the partial derivative of the expression on the right with respect to x, and then evaluate that partial derivative at the point x equal to x naught, notice that the first term, which is just a constant, would just be 0. The second term would give me a1, and the derivative of x minus x naught with respect to x would just be 1. So this will give me 1, a1 times 1, plus, what about b1? Now b1 has a term which b1 rather is the prefactor or multiplies a term of the form y minus y naught. But notice that if I'm taking the partial derivative with respect to x, then y is being held constant at the value y equals y naught. So I don't differentiate anything. And what will happen is if I do try to differentiate the right-hand side with respect to x, I'll just end up getting 0, right? So there's nothing that, there is no finite number that I'll get out of it. Likewise, the second term, I now differentiate. So I have a2, and I differentiate this second term with respect to x minus x, with respect to x. So the second term is x minus x naught square, and I differentiate this with respect to x, and I then set x equals x naught. Now, if I do differentiate this once, we will get 2 times x minus x naught. This is just like a regular derivative of x minus x naught squared with respect to x. But what I do is I set x equals x naught. And what that will do in turn is that this will make that this setting x equals x naught will evaluate or make this term equal to 0. Similarly, when we go to the term b2y minus y naught square and I differentiate, take its partial derivative with respect to x, it'll just be 0 because y doesn't depend upon x. So all the higher order terms would just evaluate to 0. And then what we're left with is just this residual term, a1, which means a1 would just be the partial derivative of f with respect to x evaluated at x naught comma y naught, right? And a sort of a simpler way of writing, instead of writing it in this manner, I can just write this as dou f dou x evaluated at x naught y naught. So you can choose whichever notation suits you. I can continue with this kind of a logic. And instead of taking partial derivatives with respect to x, I can take the partial derivative with respect to y of both sides of this expression and evaluate the resulting expression at the point x equals x naught, comma y equals y naught. And what that will do, and I encourage you to try this out, what that will do is it'll give me b1, right? So if I carry out this kind of an expression, this kind of a derivation, I'll find that dou f dou y evaluated at x naught comma y naught would give me b1. Now I can now extend this logic further to evaluate terms which are second order. So for instance, let's say I want to evaluate the term which is, let's try with the y term first. Let's say I want to evaluate b2. So now what I can do is I can differentiate both sides of this expression with respect to y, that is partial differentiate both sides of this expression with respect to y twice. So the left-hand side, we'll have dou 2f dou y square evaluated at x naught comma y naught. And on the right-hand side, the only residual term we'll be left with is b2 times 2, because we have y minus y naught square. If I differentiate it once with respect to y, I'll have 2y minus y naught. If I differentiate it again with respect to y, I'll just be left with 2, right? So that gives me b2 equals 1 over 2 times the partial derivative of f with respect to y evaluated at x naught, y naught. In the same way, I can evaluate a2, which would be 1 over 2 dou 2f dou x square, partial derivative with respect to x taken twice, evaluated at x naught comma y naught. Now, what about a term which is of this kind, which has mixed, which has a mixture of x minus x naught and y minus y naught? Well, in order to get to C2, what I can do is I can differentiate the left-hand side and the right-hand side once with respect to x and once with respect to y. So that's an example of a mixed partial derivative. And again, we have discussed this in detail in the course on Introduction to Differential Calculus, which is available on our website at very, very affordable cost. And I encourage you to check it out and give us any of your critical comments as well. So what if I focus on this expression? So we have fx comma y equals, so we already figured out a naught, a1, x minus x naught. So I'm just going to rewrite this expression once more, plus b1 y minus y naught. We've worked this out, we've worked this out, we've worked this out. Then we have a2 x minus x naught square. We have worked this out, plus b2 y minus y naught square. We have worked this out. Let's say we have this term remaining, x minus x naught, y minus y naught, multiplied by c2. So let me differentiate once with respect to x on the left-hand side. So I'll be left with, so this is a partial derivative with respect to x. So I'll have 0 plus a1. And this term will be 0 because I've differentiated this once with respect to x now. So that term drops out. This will give me 2a2 x minus x naught. That's coming from here. This will be 0 plus I'll be left with c2. Differentiating this once with respect to x will just give me a 1, and I'll be left with y minus y naught. Now I'm going to differentiate the left-hand side and right-hand side with respect to y. That's a partial derivative with respect to y. So that gives me a mixed derivative, dy dx, mixed partial derivative. So again, this term is 0. This is a constant. This will evaluate to 0. That's anyway 0. This expression only has an x now. So if I take its partial derivative with respect to y, that will turn out to be 0. So this will also evaluate to 0. It's only this term which will give me something which will have a residual. So if I take the partial derivative of this with respect to y, that's just 1. And so we're left with c2. So this tells me that c2 is tau 2f dou x, or rather dou y, dou x. And remember that the kind of functions we'll be working with, we'll assume that the order of differentiating, order of taking the mixed partial derivative with respect to x and y can be interchanged. And again, we have discussed this somewhat in detail in the course on the Introduction to Differential Calculus. So if you take the mixed partial derivative and evaluate this at x equals x naught and y equals y naught, we'll end up finding the term C2, right? So, and you can carry out this kind of an exercise also if you want to figure out higher order terms, which is if you want to figure out terms which are order 3, order 4 in the evaluation of the Taylor series expansion for a function. So we can carry out this kind of a derivation if you were to evaluate functions or rather terms of higher order than the quadratic approximation. And I encourage you to try this out as well. So all in all, what we find is that a function of two variables, perhaps two quadratic order, can be written in the form f of x naught comma y naught plus we have the first partial derivative with respect to x. That gives me the first term, dou f dou x evaluated at x naught times x minus x naught, plus we have the first partial derivative with respect to y. Again, this is evaluated at x naught comma y naught, and then y minus y naught. So that's if you truncate the series to linear order. Now notice what will happen is that if I were to truncate the series to linear order and I take this term on the other side, we have what will represent the change in the value of the function as you go from the point x naught y naught to a neighboring point x comma y. And this is how we sort of derived the idea of the gradient of a vector, right? So if I were to write this in the form fx comma y minus fx naught y naught, then the right hand side is dou f dou x, x minus x naught plus dou f dou y, y minus y naught. And thinking of this two components, or rather these two terms as forming components of a vector, which we call the gradient vector, which in this case happens to be evaluated at the location of the function x naught comma y naught, and then dotting it by the position vector, which is composed of, say, which we can write as, say, del r, which is of the form x minus x naught I plus y minus y naught j. That's the change in the position coordinates is what gives us the change in the value of the function, right? So that's the gradient vector. And again, we have derived this in detail in the course on the Introduction to Differential Calculus available on the website www.dsigma.in. Now, if you were to incorporate higher order terms as well, so then we'd have the change in the value of the function. So again, I come back to this expression. So we do have this first order term, which I'll continue to write in the form the gradient of f dot with dr. But then we also have these higher order terms, right? So this higher order terms look something like this. It's 1 over 2 factorial dou 2f dou x square. And all of these terms are evaluated at the location x naught comma y naught, right? Plus, I also have this getting multiplied with x minus x naught square. Then I have 1 over 2 factorial dou 2f dou y square multiplying y minus y naught square. And then I have dou 2f dou x, or rather dou y dou x. Either way, they'll be the same. There's a mixed partial derivative, but just to be consistent, I'm writing it in the form dou 2f dou y dou x times y minus y naught. So we have a term of this form, which constitutes a quadratic order approximation of the function, and all of this evaluated at x naught comma y naught. So that's the change in the value of the function. Now notice that if you watch the previous video where we calculated where does a function of more than one variable have stationary points, well, we found that the stationary points happen at the location where the gradient of f is 0, right? So if this term is 0, then the change in the value of the function, so if I'm around a stationary point, rather, if x equals x naught comma y equals y naught is a stationary point, then this gradient of f will be 0. So the linear order term in the Taylor series expansion of the function drops out. It is 0. So the change in the value of the function is then given by the term in this square bracket. right? This is what will give me DFF. And if I now want to figure out whether the stationary point that we've identified is a minima, a maxima, or a saddle point, I need to understand when, under what conditions is this term, this entire expression inside the square brackets, whether is it positive, whether it's negative, or whether it evaluates to zero, right? Now, this looks like a somewhat messy expression. Now, how do you make sure that we can write it in the form that it's positive? If it's positive, if the right hand side is positive, then df is positive, which means we might have something like a minima. If it's negative, we will have something like a maxima. If it's zero, then we'll have something which is called a saddle point. So in the next part of the video, let's try and figure out how I can maybe do something with this expression to really point out the nature of the stationary point, which is nature of the behavior of the function around a stationary point, and a stationary point by definition is when the gradient is zero, gradient of the function is zero, and the nature of that stationary point will be given by this quadratic approximation to the function. So hopefully this video is been interesting for you, and I'll follow up with the next part of the video where we sort of explore this idea a little further. Thanks for watching.